Okay, welcome everyone to the NASA Alumni League virtual meeting. It's November 4th, 2021. I'm Stokes McMillan, and today our speaker will be Jason Ballard. Jason has dedicated his life to working big problems in service to humanity, and most recently and notably as the co-founder and the CEO of ICON. ICON is based in Austin, and it's a construction technologies company using construction scale 3D printing to tackle the global housing crisis and prepare to build on other worlds. Now, in fall of 2020, ICON was awarded a research contract through the Air Force, and this included funding from NASA to begin research and development of an off-world construction system planned to support future exploration of the moon and beyond. Now, prior to co-founding ICON, Jason Ballard served as CEO of an eco-friendly home upgrade company that normalized sustainable and healthy approaches to home improvement. So Jason hails from East Texas, and he studied conservation biology at Texas A&M. And he's currently enrolled in a master's program in space resources at the Colorado School of Mines. And he lives in Austin, Texas with his wife and 4 children. So Jason Ballard, welcome to our program, and let me hand it over to you.
Perfect. I'm happy to be here. And yeah, that pretty much covers it. That's great. Before I get into my presentation formally, I just want to say what an honor it is to be here, because becoming a truly spacefaring civilization, learning about our place in the universe, exploring the universe with robots, and hopefully one day with human bodies, is a long-term, large team, almost civilization-wide endeavor. And I am incredibly conscious of the way that I am standing on the shoulders of the work of the very people on this call. And so it was easy to say yes to, and it's a delight to do so. What I get to do has been made possible by the work of all the folks who have come before me in the field of aerospace. So I'm going to get started on a presentation. I'll kind of quickly introduce ICON and then spend most of my time talking about what we're doing to develop off-world construction systems in partnership with NASA and others. And then I'll try to leave plenty of time for Q&A. But if you don't have any questions, don't feel like you have to. So I'm going to share screen. Stokes, I might ask you to make sure you can verify that everything's coming up appropriately. So are we seeing the screen okay?
Yep, looks good.
Okay, I'm going to go to full screen and make sure it will allow me to advance appropriately. It's saying it won't. Let me try one more time. Perfect. Does that slide advance?
Yes, that advanced.
Perfect. Okay, well then I'm going to carry on. So ICON was originally provoked into existence. I say provoked intentionally by the global housing crisis. In the United States alone, we need about 3.3 million homes per year, and we're only building about 1.3. And so we're going about 2 million homes into the hole every year, year after year. And so this is leading to price increases, quality decreases, all kind of sustainability and resiliency issues. And it's a really, really big problem because human shelter is a basic need. It's like Maslow's hierarchy of needs, like very fundamental, right there with like food and water. The building industry is the #1 contributor to almost every environmental issue that we can measure. And from a macroeconomic perspective, the entire industry, which is the largest industry in the world, is going backwards in terms of productivity. And this is not what we want at all for an advanced civilization. And if you sort of expand the scope broader, like outside of the United States, about 1 in 7 of our sisters and brothers in the world do not live in housing we would consider adequate. Anyone on this, another way to say that is like, if it was someone you knew and loved, you would not accept it. And so this is a crisis, the global housing crisis. That's what everyone calls it. And it's related to, I mean, we've been building houses and structures the same way for about 1,000 years. And that is not CEO hyperbole. You could Google, while I'm doing this presentation, if you'd like to Google a 1,000-year-old home, you will find that it is made of lumber and bricks or stone and mortar. And we're sort of, that's exactly how we build to this very day. And it kind of got us out of the caves and temporary shelters, I suppose. But we've now reached the limits of what this approach to shelter can do. And we believe at Icon that it's time for the construction industry to join the digital robotic age. And so we're a construction technologies company. That's exactly what we do. We work very deeply in robotics, in developing our own software to control those robotics and the larger construction process, and in the advanced materials necessary to make all of that happen. So we don't outsource any of that. We have like very deep subject matter expertise in all of those areas. We have PhD level, multiple PhD level employees in all of these areas. And I think we actually have 12 ex-CEOs that work at Icon. Another way to say that is like, I'm not even close to the most impressive person who works at Icon. I'm just the most excited. And so that's why they let me do these presentations. But the big point about Icon culturally is we really are trying to develop these technologies and use them to serve the world around us. Like, we are a company in service to the world. The primary form of that service has been in housing. Here you can see an example of what it looks like for our Vulcan construction system to be deployed out on a home site. This is a house that I'll show you more about in a minute in the presentation that we printed in East Austin. We can print houses about 40 feet wide and 12 feet tall. The way that we got to those measurements was working with our development partners. This printer will print over 90% of single-story homes in the world. And so this is sort of like where we started, like single-story housing. We've developed, again, our own construction operating system. So all of these robotics are operated with a phone or a tablet. We actually have a mission control where we can remote operate and control the printers from a long way away. This will be very important in our work with NASA in the future. And then the material science that we use is inherently more sort of resilient, strong, and high performing than a lot of our conventional building materials. I love wood. I think wood is very lovely, but wood also wants to catch fire. It wants to mold. It wants to be termite food, and it's a conductor of heat. So often, like, you're working against the fundamental properties of wood with regard to what you want a building to actually do. And by working with these extrudable masonry materials, you're more naturally cooperating with the behaviors of those materials. And so the result, why we're so excited about 3D printing from a terrestrial perspective, is that it's faster, right? We're able right now to print like a normal sized American home in about a week. And there's some finish out and stuff, of course, but that process of delivering the wall system takes a conventional builder 4 to 8 weeks, and we do it in a single week. That alone lowers cost, but of course, automating out all those trades and using a single material supply chain also lowers cost. We do all this without compromising customizability. A lot of the approaches to low-cost housing in the past, whether it was trailer houses or prefab houses or modular houses or shipping container houses, really reduced design freedom. With a 3D printer, if you printed 100 homes in a row, all 100 can be different. And in fact, if you wanted a house in the shape of a Fibonacci spiral, we could print you a house in the shape of a Fibonacci spiral. It expands rather than contracts design freedom. This will also be very important when we get to off-world construction in a moment, that you can build almost whatever you need and whatever you can imagine. Because it's robotics, it's scalable. Again, the buildings we're building are more energy efficient, they're more resilient to the elements. And so you're getting, usually when you lower the price and increase the speed of something, you get something worse. My grandfather used to say, there's nothing somebody can't make a little worse and sell a little cheaper. And that's not what's happening here. You're getting a better building at the end that is more affordable and delivered more quickly. And then, of course, if you all have ever been to a construction site, often it looks like there's more waste than house. But with 3D printing, you print what you need to the drop, and then you stop. And that's cool, not just because it rhymes, but because construction waste is the #1 contributor to landfill waste. It's our most wasteful thing we do as humans, is construction. And so that's a big problem. And so all of these things sort of get solved simultaneously when you move the paradigm to robotic construction. Just to show you, this isn't all just like a fancy hand waving. A few projects we've delivered. The first one is in 2018, we delivered the first permitted 3D printed building in the United States, probably in the world. It's harder to verify, but for sure the first one in the United States. That house is still standing and occupied today. A gentleman named Taylor lives there. I check in with Taylor all the time to see how it's going and what we can learn. But this was really the moment for us when people realized this wasn't science fiction, that this really could be possible. We then printed a very similar house about a year later, same floor plan, twice as big, but we delivered it in half the time. So an overall 4x improvement in construction performance. We then printed a series of homes for people experiencing chronic homelessness in Austin, Texas. These houses, we set up the printer and we printed them 3 at a time. And all 3 have different floor plans, which is a thing that's very difficult and expensive to do with conventional building methods. This project's, about 2.5 years old now, but you can see even then, the person who lives in this particular house, this gentleman, I mean, his other option were like a used trailer house or continuing to live under a bridge. And these are homes that like any of us would be like quite happy to live in. I mean, my family of 6 would have a hard time fitting in this particular house, but in terms of their quality, their comfort, and their beauty, and their resiliency, it like unbelievable to be able to deliver this quality of construction at this price point. We delivered the first 3D printed community down in Mexico. This project was notable because it was actually in a seismic zone. And the region has actually received a magnitude 7.1 earthquake that caused extensive regional damage and 0 damage to the 3D printed homes. It turned out the safest place to be in Nacajuca, Mexico during that earthquake was in one of our homes. And how seldom that's the story for the very poor, right? They're usually the very last people to receive advanced technologies and advanced building materials. And so this was a project we were really, really proud of. It was actually documented pretty well on a TV show called Home. If any of you have Apple TV, there's a show called Home, and I think the season finale was about this project. So if you want to know more about it, you can look it up there. We also have a large contract with the Department of Defense and multiple military departments. As you can imagine, they're highly interested in the rapid deployment of resilient infrastructure. Typically, the Department of Defense, whether it's domestic military bases or forward operating bases, or their choices are like very fast but very unsafe and temporary shelter like tents and prefab boxes, or the more resilient things like permanent bases and permanent buildings taken like literally an act of Congress and years to get on the ground. This particular project where we showed up to a remote part of Camp Pendleton in California, and they didn't tell us what they wanted us to build till after we showed up. That was kind of part of the drill. So we showed up and they're like, we want a vehicle hide that a missile launcher can park under to be safe. You have 2 weeks to build it, go. And we printed it in 3 days, and then the team went swimming in the ocean. And so there you are, there it is kind of going inside. So that relationship is progressing really, really nicely. And it was through a funding vehicle created by the Air Force, AFWorks, their innovation command, that we first received our first NASA funding, and I'll talk about that in a minute. Continuing to work with the military, we're now doing a lot of work replacing aging domestic military infrastructure. We have lots of barracks all over the United States and other military buildings that are like very, very obsolete and aging and decrepit, and certainly not worthy of the sacrifice that the women and men in uniform are making on behalf of this country. And so the first barracks that we did in the past year is the largest 3D printed building in the Western Hemisphere, it turns out. But now we're going to be doing a series of these. This, I won't watch the whole video, but some of you may have been wondering, like, what does it look like when you 3D print? So this is a little bit of a video. It'll show one wing of that barracks going up. It's being printed in this particular video by a printer, like kind of 2 generations old printer. You can kind of get a sense of how layer by layer it follows the floor plan. On this particular project, it was in a bunch of wild weather. Any of y'all remember the snowpocalypse, the big snowstorm that hit the state of Texas last year? When we started this project, it was like in the 80s, and then that snowpocalypse happened in the middle of this project. So our printer has printed as cold as 36 degrees and as warm as 105 down in Mexico. So the environmental range is quite large. You can also notice like how many people are not in these photos. It's mostly just like engineers and staff just kind of monitoring what's going on. We're really proud of this project. The DoD, you can see some of the old aging barracks in the background there that we're replacing, and we're very, very pleased. Most recently, the most recent project that we finished that was announced was our first market rate housing in the United States, the first 3D printed market rate housing in the United States. And so like it was an infill development in East Austin. These homes were sold at market rate, and 3D people can get mortgages for 3D printed houses. And this just represents a load of progress from us, and the quality of the prints. This was just like a really big moment for us, and we're super proud of it. Almost through with the Earth stuff, so we can get to the fun space stuff. We're in the process of finishing up right now a house that we call House Zero, and this is a house we're using to really advance architectural possibilities, because for a long time, as you can see, the customers who have hired us, they've ended up asking us to print houses that look a lot like the houses they're used to. And we've always thought this was sort of a shame because 3D printing opens up all these fantastic new possibilities for shapes and architecture, because a curved organic form is the same price and difficulty as a straight line. And so you can see we've really incorporated organic forms. These things sort of look like very premium high-end finishes and approaches to building, but they're like very straightforward and simple for the printer. And in fact, those ripples in the wall actually make those walls stronger. Much like if you had a flat piece of paper, it would fall over, but if you fold it, the paper will stand up. We can use the shapes of the walls to make them stronger and more beautiful at the same time. So very, very cool stuff. And then most recently, you may have seen in the news in the last week, we just announced that we're about to do a 100 home community in the Austin, Texas area, where we're going to deploy a fleet of printers. We're doing this in partnership with Lunar, who's the largest home builder in America, and we're very, very excited about this project. But as I said, we're trying to put this technology in service to humanity, and part of that is solving big problems, but another thing is opening up profound opportunities. And so we have been working with NASA since the very year this company was founded. That very year, NASA had a Mars 3D printed habitat centennial challenge going on. So we partnered with the school where I'm doing my graduate studies, the Colorado School of Mines, and we participated in that contest. And we were an award winner and a finalist. And that opened up the door for us to begin developing this technology for space much more aggressively. More recently, sort of the conclusion of that Mars journey was the Johnson Space Center in Houston. And I know Stokes is familiar with this, and maybe some of you are as well. They wanted to build a Mars analog habitat that really resembled the kind of permanent infrastructure we might deliver on Mars. And they believe it'll have to be delivered with robots using local materials. And so they commissioned us to design and deliver a Mars analog habitat that they're going to use to study long-term human health and performance, while astronaut analogs will live there for a year at a time, 8-minute communication delay, the whole 9 yards, to begin researching the effects on human beings for long duration space exploration. And so this is very cool for us. I mean, it's like we really can build off-world construction project using off-Earth analog materials, and we can do it robotically. So we're like very, very proud of this project. I hope you all get to see it. Being inside of it, it has the feeling of an advanced but extinct civilization like left a temple here. So, I mean, it has like it's very cool to be inside. We're done with the print now, so we're doing all the mill work and finishing out the thing soon, and they're going to start missions in it next year. It's also very cool as a space nerd that like a lot of the pictures of human beings getting ready to go to Mars will like take place inside of an icon building. And so like for a skinny kid from East Texas, it's definitely like this like pinch me moment. And it was cool to be able to do it in Houston, which is like very, very near where I grew up. So very cool. But the most long-term and
to have raffles at rodeo that passed by a vast majority.
maybe
Someone has a hot mic.
Okay, we got it. The most long-term of our engagements with NASA is something we call Project Olympus. And that is our attempt not to use our Earth-based printer, which you saw on this one, where you know, if you see the left inset printer there, we're using our normal Earth-based printer. This is the development of a
religious service.
Somebody's got an open mic. Let's see if we can get that squared away.
Hey, Mary Ann, could be you. We're hearing somebody. Everybody needs to go to mute, please.
If you have questions, I can't wait for them. So look forward to hearing your lovely voices very soon. But our most long-term engagement is on the Project Olympus. And this is the wanting to dedicate some effort to developing a purpose-designed off-world construction system. It has to fit in the payload of a rocket. It has to conform to certain like mass and power requirements. And it has to use the local materials of the moon and ultimately Mars to do its work. And so this is the project that we call Project Olympus. And we're contracted with the Marshall Space Flight Center to do this work. The NASA Center for Advanced Manufacturing and Construction is at Marshall. And so they're taking the lead on these off-world construction technology developments. As part of that program, we've already demonstrated a 3D printed rocket pad. They believe that rocket pads will be some of the most important early pieces of infrastructure that we need if we're going to go to the moon to stay, right? If you return over and over again to the same spot, you're going to blast a crater in the surface of the moon. And not only that, like some of the mass of the new modern landers requires so much thrust during landing that the ejecta from the lunar regolith can actually reach orbital velocities. I mean, it could really make a big mess if we can't contain the dust and the effects of landing repeatedly in the same spot. And so we created this 3D printed rocket pad that has this cool internal structure that's meant to defray the exhaust in ejecta. And we actually strapped an M-class rocket motor to it to see how it would fail. I hate to spoil the ending, but the rocket pad did not fail. But we had a lot of sensors and we were able to grab a lot of data. And I believe there'll be a scientific paper coming out about these results in the not too distant future. But we've now at least confirmed in an Earth analog, in an Earth environment, that we can 3D print a rocket pad, a landing and launch pad that could withstand the kind of thrust you would expect of a lunar lander and launch vehicle. So that was very cool for us. And so all of this makes us feel like there really is something for us to do here. And not only that it's cool to do, but it's important to do. I truly am part of that camp of people that believe becoming a spacefaring civilization is the most pro-human, optimistic, pro-future thing that you can do. It's a thing that we need to do, not a nice to have, but it is a long endeavor. So we're going back to the moon to stay, right, as part of the Artemis program. That's the program now, and so that's what we're building for. But we feel this like great responsibility, because what we're talking about is humanity's first, not our first camping trip, but like our first like true home on another world. And I kind of can't believe I get to work on this. And it's really not only scientifically and interesting in engineering from an engineering perspective, it's a very romantic idea. And so it's like the coolest project you could ever hope to work on. It's a big trick, right? The moon is not slightly different. The moon is a lot different. In fact, there's a lot of ways in which Mars would be easier. Mars has an atmosphere. Mars has more gravity. So on the moon, we're dealing with micrometeorites that rain down at about 180 kind of per square kilometer every year. They have no atmosphere to burn up in. They all come down, and they're at like ballistic velocities. The lunar dust, I don't know how much you all have ever been familiar with the lunar dust. It's brutal. The Apollo astronauts said it was the worst and hardest challenge of the entire Apollo program, was managing the lunar dust. 100% of seals during the Apollo program failed. Everything from the seals on the astronaut gloves to the seals on the doors. These were seals that had been tested for thousands of hours on Earth, and they failed after 13 or 14 uses on the moon because of the dust and the abrasiveness of the dust. There's no weathering on the moon surface. It's like micro razor blades. And on top of that, they can get electrostatically charged and levitate and float. And it's just, the moon dust is crazy. It's a different world. And so most technologies in the arts are being designed to avoid the dust. We have to actually handle the dust and build with it. And so it's quite an engineering challenge. The radiation environment is very intense and can mess up some of the advanced electronics and computers that we're going to need to stay. There's these solar particle events, extreme temperature swings, right? The Apollo program, the astronauts always arrived and left before a lunar day had passed, even half a lunar day had passed. To stay on the moon, we're going to go through 14 days of lunar day and 14 Earth days of lunar night. And the temperature swings are 500-degree temperature ranges. And very difficult to get anything to work on Earth in an oven and also in a freezer. But that's just going to be pretty table stakes on the moon. The moon also has moonquakes. They're very frequent. They're not as intense as earthquakes, but moonquakes ring. The whole moon rings like a bell, and they can go on for like an hour. And so how do you build buildings that can handle getting rung like a bell for an hour? And then, of course, close to zero atmospheric pressure. So a real challenge to build in this environment in a way that would be safe for human beings. I do believe, as we go back to the moon to say, there's going to be all kinds of approaches to building and habitats and things. There's going to be the landed habitats like you saw during the Apollo program. I think we'll see some inflatable habitats like if you've ever seen the Martian movie. And there'll probably be all kinds of specialized systems to do things. But 3D printing has some real things going for it. Number one, as I'll show you in a minute, we can use 100% in situ materials. They call it ISRU, in situ resource utilization. All we have to bring up is the printer. We don't need binder. We don't need extra stuff to mix with it. That reduces the mass and therefore the cost and risk of the program tremendously. If we can use the local materials of the moon to build all of the things we need. This is how all exploration in the past has succeeded. When humanity was exploring the globe in the past several thousand years, if they tried to bring home with them, right, the explorers who brought all their wine and their whiskey and their harmonica and their piano, those people didn't make it. It was the explorers who learned to live off the land, who were successful ultimately. Also, with this single system, you have, with a 3D printing system, you don't need a special road maker and a special brick maker and a special habitat system. It's one system that can make launch pads, walls, roads, berms, unpressurized buildings, pressurized habitats. That's much more simple from an engineering perspective. And it's also more cost effective for the taxpayer in terms of minimizing the overall cost and therefore bureaucratic risk to going to the moon, to say. Also, when you're building out of these like geological materials, you're going to have a safer building than you would have from like a thin metal structure and inflatable habitat. This is going to protect you from micrometeorites, the radiation, the thermal changes. It's a safer building. So ultimately, when you add all this together, it's more simple from an engineering perspective. It's more affordable. You get a more safe and resilient result. I think this is not a neat thing to have. I think we have to have it if we're going to become a spacefaring civilization. We have to be doing robotic construction using local materials. Full stop. I don't think there's another way to do it in the long term. To give you a sense of what I mean by these costs,
That's alumni, JC.
we ran the numbers. I think we got another hot mic.
Who's that?
What's his name?
Yeah, who's, I don't know what is.
What he's talking about is.
Hey, we got
On the
another
book.
hot mic.
Dave Hansen, please mute your mic.
Oh, sorry about that.
No worries. We actually ran the numbers on if we'd taken the dry material of that first little tiny house we built, if we'd taken that up to the lunar surface, how much would it cost on rocket fuel? Like how much would it cost just to deliver it to the surface, not build anything? And the result is about $1.4 billion to deliver the materials sufficient for a 350 square foot structure to the surface of the moon. I know real estate in San Francisco is expensive, but this just sort of puts it to shame. We're never going to have a moon base this way if it costs $1.4 billion every time we want to build a tiny house. And so that's not going to be an option. We're going to have to use the local materials. And so you can see in some of these visualizations what I'm talking about. Every road, every landing pad, every wall, every structure you see in these imageries, we have already designed, and they're designed to be built out of local lunar regoliths with technology. You can see some concept renderings of the construction system itself. We've chosen this boom tower architecture. That way we can reduce the mass. It's been designed to fit on all of the major landers, whether it's Blue Origin or SpaceX. It's been designed to fit within the power constraints that we expect to be present on the moon. But I'll show you. So the phasing from here for us is we're scheduled presently to go to the moon in late 2026 to demonstrate the core subsystems. And I'll show you some of those subsystems soon. That will then open up full-scale demonstration in a phase 2, and then hopefully the moon base gets underway in a very permanent way. And the rendering you see in the background was a moon base design that we spent a lot of time on, and that I won't go into all in this presentation, but it's situated on the edge of a permanently shadowed region of the moon where we do believe there's water and other volatiles present. So that's probably where you'd want to situate a moon base. We've used a Steiner tree architecture for the road layout to minimize the amount of power material needed to build those roads. And everything you see in that picture in the background is buildable within the dimensions of the Olympus system that you see. So I mean, this is like as close to real as it gets. We've run all the thermal calculations on those buildings. We've run the stress calculations on those buildings. You're looking at like, I'm not saying this is what NASA will build. I'm saying what you see could be built. Nothing in that picture is science fiction. And so we're excited about what all that could mean. And I want to talk a little bit more about the actual processes we're using to take raw lunar regolith, the local soil, and to actually turn it into a building material. That's sort of most of our work right now. Our two favorites, I'll start with my favorite, is a laser directed energy deposition, where you're actually like using a laser to melt the lunar soil and turn it directly into a building material. That's the laser we've developed in-house. We're now putting it through dirty vacuum chamber testing, but we've been loving all the results that we've been getting. This is like a benchtop test. You can see like where it like, you would deposit the regolith and then you would center or melt it into place. And the result is a building structure. So we've been doing this at a small scale, as you see there, and we've slowly been turning the scale up, 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 and up. The object there next to the Dr. Pepper can, that is the largest object ever built out of simulated lunar dust. It's unbelievably hefty and strong, and we're actually submitting that sample now to NASA for a lot of testing on how does it actually buffer radiation and some of those other things. But we are very, very pleased with the results that we're getting, both in terms of their strength and the power requirements. That little ring you see on the left, we produced that ring with 80 watts of energy in a laser. And so like we can do these with the kinds of powers that we'll expect to have. And I'm very, very optimistic. The other big area of research for us is just straight up melting the lunar regolith. If all else fails, almost every material in the universe will melt. And so are there highly efficient, furnaces, for lack of a better word, that we could use to melt the lunar regolith and just extrude it, almost like melting the plastic in the desktop 3D printers you guys have seen. This research isn't quite as advanced as the laser research, but we're liking the early results we've gotten. And it'd be nice if we had sort of two different choices we could use for different applications. The laser, as you might imagine, is much more precise, and the melting might be more useful for like bulk building projects like walls or blast shields and things where precision wasn't as important as just delivering a bulk of material into a built object. And so, of course, have been like quantifying all our samples, and they are incredible, like both with the laser and with the outright melting, we're getting incredibly strong samples. As high as almost 30,000 PSI, we're averaging close to 20,000 PSI. The weakest we've tested was about 13,000 PSI. To put that in perspective, the concrete that the Air Force requires for a runway to land a military jet on is 4,000 PSI. So we're talking like unbelievably strong masonry ceramic material. And so again, all signs point to like, this is very promising direction. There you see a rendering of the test that we're scheduled to do in 2026, where we will put the laser subsystem and possibly the melting subsystem as well on a CLIPS lander and demonstrate built construction specimens on the lunar surface, and then sort of hopefully take that subsystem all the way up to TRL 9, which will unlock the development of the full system. So that's what we're up to. We've got a ton of amazing partners, not just NASA, but the Air Force, the Department of Defense, the Marines, a bunch of really wonderful investors who have been incredibly supportive, some of the best architects and builders in the world. And you won't meet a more optimistic person than me that we can have a moon base if we want one. We can afford a moon base if we want one. And I hope that's exactly what happens. So that's the end of my formal presentation. I'm happy to take questions and just see what's on your mind and where we go from here.
No, outstanding, outstanding. So my question is, what about say insulation? Domestic houses? How thermally insulating is your material, or do you have to put insulation between layers?
Yeah. So a few things to say. The bulk regolith has very high thermal mass. So we're of course going to need some life support systems in here, akin to what you'd have on the International Space Station. The question is like, how powerful do those systems need to be? And our calculations show that at about 2 meters thick of wall, which is quite thick, we can do all of the radiation shielding, micrometeorite protection, and thermal insulation we need to do, sufficient to keep the habitat stable and livable with current life support systems. So we need about 2 meters thick of it. The way we would actually deliver that to be efficient with time and power, it's almost like we would print the formwork and then fill the interior with loose bulk regolith. Like you don't need to melt it and center it all into place in the interior. You almost just need to like print the formwork and then just fill it with loose bulk regolith. That's another thing that the print system that Olympus system we've designed is capable of doing. You can sort of slide the laser subsystem out of place and it can just convey loose regolith straight into whatever built object we need to convey it into. So that's actually probably how it would go down. I might even see if I have some pictures of that while we're
I have a question.
Yes, sir.
So do you run the utilities, electrical and so forth, outside the walls or inside?
So the both the life support systems and the lunar power utility, whatever that form that ends up taking, are going to be projects that other people will take, and then we will design to integrate with those systems. So like we haven't been given the contract for the formal development of those things. What NASA has told us is the power we will need will be there when we need it. And so I expect what will happen is like the life support systems will be contained inside of the structure, but there will have to be a piped in power source, whether it's nuclear or solar or some combination of the two, that'll be used as the external power source to the actual habitats.
So Jason, and so you talk about essentially the utilities being integrated. You know, what's really difficult in a space environment, of course, you might just consider this an immovable, non-flying spacecraft, that you be able to maintain it easily internally. And so is there a design option that would allow you essentially to put all this, you know, all the utilities, if you will, so you don't have to actually break through the internal wall to access them?
Yes, that's exactly right. It's kind of like you're right. The International Space Station, it's just a space station that happens to be sitting on the surface of the moon, is a really good analog for this, of like making it very easy to access all of the life support systems and major elements of the utility without burying them inside. It's almost like we need to create a big space that is shielded and sealed, and then all of the outfitting happens internal to that space. So that's how it would kind of go down. Trying to show, so we have done some research on this. I'm trying to see if I can find one of those presentations fast enough, because I think there's some things you all will find interesting in that regard. But I'm happy to take other questions while I search for it in the background.
Sure. While you're searching, do you have any chopped fiber or anything like that add tensile capability?
Amazing. Yes, in our terrestrial concrete, we do include a glass fiber. We've researched glass fibers, steel fibers, carbon fibers, and other kind of like exotic polymer fibers. And believe it or not, fiberglass is the big winner. There's no demonstrable, there's not enough of improvement when you jump to steel or carbon fiber to justify the extra costs and other risks associated with using those materials. And so that's what we use. And the good news was like, that's also the cheapest. So like the one that won from an engineering perspective was also just like, good luck for us, was also the most affordable. That's not always the case. I might, unless somebody has a burning question, I might flash up. I focused mostly on the engineering today, because there's been some interesting questions. I might flash through really fast an architectural presentation. I'll just really scream through it and highlight some of the major things. Is that okay to do, Stokes?
Yeah, we've got plenty of time, Jason. I think we're all.
Oh, amazing.
In
Can you see my screen once again? We kind of played this game once already.
Yep, we see it.
Okay, I'm going to try to enter full screen and see if that works. I won't show you all. This is a very long presentation. I won't show it to you all, but just to show you the kind of work that we've been doing. We did study all of the major Apollo missions, every landing site, both robotic and human. We've looked very closely at where the water's confirmed. What do we know about the geology in those areas? Because that's going to be, like in the Mare regions, it's very basaltic, and the polar regions to be very feldspar rich. And so those materials would behave very differently. And so we thought a lot about everything we could find out about what the site might look like. NASA hasn't announced where the location of a moon base might actually be. We've studied a lot of other architectures, Earth-based, of extreme environments, like how humans have learned to live in other extreme environments on Earth. We've really tried to understand, will we be able to harvest the regolith we need at a fine enough particulate to process it properly? Again, we're standing on y'all's shoulders. There's so much wonderful engineering and geological research that has been done. This is some of the moon dust stuff I was telling you all about. It's really aggressive, nasty stuff. I showed you laser and extrudable melting today. We've also looked at microwaves and other approaches. We looked at a bunch of form factors for the actual printers. We looked at a number of geometries for lunar architecture. We've thought about all the major infrastructure elements that will be necessary to have a moon base: roads, landing pads, berms, and blast shields. to make sure we were designing a system sufficient. We thought about how those things might be built and in what order and how they might be arranged. This is that Steiner tree thing I was explaining earlier, that if you lay everything out in a square, you need one amount of roads, but if you like lay it out in this like Steiner tree orientation, you actually can reduce by about 15% the amount of stuff you have to build just by optimizing. This comes from like circle packing mathematics. We've thought about the size the landing pads need to be based on everything we know about the thrust of the approved landers. And we've sort of thought about phasing, where you would initially have a lander, and then you would sort of put some like repeatable roadways around that lander so you weren't always handling the lunar dust. You'd want to very quickly move to landing pads that could connect to the original habitat. So all this has just been flown up so far. But then eventually you want your ISRU infrastructure, but then eventually you have your first building that you build on the moon. And then you can begin expanding the clusters of habitats, and then ultimately sort of end up with this little, like, almost like in Antarctica, like this little like lunar hamlet on the edge of this permanently dark area. And I think it's, I think it's like a really cool thing to imagine. Again, we've really looked deeply at the radiation doses, what amount of shielding we'd need, how we compare to inflatable and hybrid structures, what the ideal shape would be. We've studied other inflatable structures to make sure we were as good or better. We've thought deeply about the shielding and pressure requirements, because all the pressure is going the opposite. It's basically a big pressure vessel. The strongest thing is a circle, but we can't print circles. And so what's the optimal angle to print? How thick does everything need to be ultimately to protect from everything we can imagine? It ends up being about 2 meters. We've then said, what are the most optimal volumes? Is it a torus, is it a dome, or is it vertical cylinders? We've analyzed these things in terms of both usable area for humans, the amount of energy and material needed to create those structures. We then submitted those structures to various kinds of testing to understand the way that they would perform under the stress. We studied every kind of analog, whether it was the International Space Station. We studied like, well, what do they like and not like about the International Space Station? We studied nuclear submarines, the Antarctic Space Base, trying to understand what makes spaces good or not good when you're living for a long time, right? So the ISS, the McMurdo Station in Antarctica, US nuclear submarines, how big are they? How are they laid out? What do they need? How do they support life? And there was a ton that we could learn, and we applied all that. And ultimately what we ended up at is like the optimal structure is this like torus shape. And at first we sort of were experimenting with, what if you just printed it and like piled the regolith on top? And that's kind of what you see, just pile the regolith on top. That seemed both problematic in terms of the lunar quake and like the erosion, like very long-term and very slow, but some erosive properties. We've thought about how we would actually go about constructing things, different approaches to the construction, space planning. Again, I'm going very fast. All of this we could talk about for a long, long time. This is radiation doses in the, you'd want to shield the sleeping areas more than the working areas. You spend a ton of time in the sleeping areas. Where to store water. And we've tried to think really, really hard about this. And where we ended up really starting to head, as you guys saw some of the other things, is this idea of like over on the far right, printing formwork that is then filled with regolith. And that formwork actually can add tensile strength as well as optimizing and retaining the regolith pockets for certain areas. And so, you guys know about lunar days versus Earth days, how to light the space, how to make it to where humans can actually, you're not going to want to bring your spacesuit in. You're going to need to crawl in and out of your spacesuit. So you don't ever bring dust. No dust should ever go inside the habitat. So you're going to want to crawl in and out the back. That's sort of the architect. That's one of many architectural presentations. The reason we went through such a thorough architectural exercise is to make sure we were designing a system that could deliver what would actually be needed. It's like, we're actually not even the architects. We did all that just to make sure we're designing our system appropriately. And I probably said this 10 times already, but like, we can do this. Like this is like, we're really trying to be thorough and rigorous, and this is doable. So there you are. I saw something pop up in the chat. Oh yeah, mute your mic. Yeah, that's right. Stokes, anyone else? More questions?
Yeah, Jason, thanks for doing this. This is really interesting.
Of course.
how level and how smooth of a surface would you need to start with on the moon, and how would you do that?
Yeah, we haven't analyzed the absolute extremes. The answer, of course, the answer is like the smoother the better. The Kennedy Space Center is working on excavation. Rob Mueller and a few other folks are over there, and I'm very encouraged with the progress they're making. I think we will need excavation even in the smoothest of spots. We'll it'll be a team effort. We're on the construction, somebody else on excavation, somebody else on power systems. And this symphony, all the trains are really going to have to come into the station at the same time. That was a long-winded way of saying like pretty smooth if we can get it, but not absolutely smooth. So.
Could you give us some contact information if we want to get further information?
Oh yeah, I'll type it in the chat. The easiest thing to do, that's my email address, jason@iconbuild.com. That's the most straightforward thing to do. And we can take it from there. Yeah, if any of you have thoughts or connections or other research that we should be looking at, I mean, we are all ears, and there's no sort of pride of authorship. Like one day I'll be dead and gone. Nobody will remember I even live, but I hope there's a moon base. And so all the help we can get, we want it.
Jason, a couple of questions for you. You talked about the compression strength of the material. How does it compare to concrete in terms of tensile strength? And notoriously, concrete's not a good tensile material, but yeah. Could you use this for bridging structure across building a beam or something like that?
Yeah. While I answer this question, I'm going to pull up one more presentation to like illustrate what I'm about to tell you. The short answer is what we end up actually making with the laser is more akin to it is a ceramic rather than an actual concrete. And so the ceramic does have higher tensile strength than a concrete, but it's still not as good as like a metal or a lumber or any of that kind of stuff. And so let me make sure.
And where I was going there was, building a bridge across a crevice where, you basically don't have a way across a gap, but you could build a beam that you could extend across.
And so you're exactly right. Actually, I have it on my shelf. I'm just going to grab it off my shelf. If y'all can hold on just a second. I'm going to show you something. Can y'all see this sufficiently? So this is a design of that habitat. I've 3D printed this on my printer here in the office. And you can see all those pockets, right, where you would put regolith in there. This shape looks really pretty, but the pretty is actually not the point. We really did this like study of like old cathedrals and other kind of for a long time, humans knew how to build with materials that only had compressive strength. And they would use flying buttresses and arches and domes and vaults and sort of things. And so what we've done here is we've used a compressive material and laid it out, oriented in such a way that all of the forces get transitioned into compressive loads.
Sure.
My hunch is you could design a bridge using a very, very similar principle. And so it's funny, we have to look at these very ancient building methods before we had rebars, and there's a lot to be learned. It's a very rich area of exploration, I think, that we haven't done a ton, but we've done enough to validate. We simulated this very heavily. There's almost no tensile loads in this whole building. It oriented on compressive directions.
The other question I had in the illustrations of your construction technique, do you start by sintering or building a floor somehow out of this regolith material so that you have a dust-free, smooth floor surface?
That's exactly right. That's exactly right. That's almost how you would build roads as well. The roads are actually fairly straightforward. Is that you just sort of drive and center as you go, and you get an initial sort of dust-free work and travel area. And I think that kind of infrastructure of just dust-free areas, or at least dust-mitigated areas, will be some of the most important early infrastructure that they'll have to have. Because that dust is nasty.
Thank you.
Of course.
Well, what about the machinery to build all this stuff? How do you propose to get there? It sounds like the bigger the structure, the bigger your sintering machines and laying down all the material,
Yeah.
is your,
Well, we were actually not really, but like moderately anxious about this because we started working on all this before NASA had chosen lunar lander partners. Now that they've chosen SpaceX as the primary early lunar lander, at least for humans landing systems, I think there'll be another competed contract for cargo landers. But we're even our most aggressive designs are like well within the mass tolerances of the landers that it looks like we're going to need. Now that means we're limited to like single story structures, right? Like if you wanted to build 2-story, it's just easier to build low buildings. It lowers the mass and the complexity of any engineering systems. And so we are grateful that NASA chose to fund landers with fairly high mass capabilities.
so right now, is there a maximum size you can build?
Yes. So we sort of oriented the way we got these designs was like we were trying to poke NASA, like, how do you guys not have a moon base plan? That's your job. And so they gave us some like rough parameters. They were like, well, maybe the early missions would have an astronaut crew of 4. It's like, well, how did you get to 4? It's like, well, that's the mass of human beings and equipment that the current landers could support. It's like, okay, that makes sense. And so we really optimized everything for 4 humans. And then again, with our study of submarines and International Space Station, we tried to say like, what would the optimum space be for 4 humans to live for 6 months? And then that gave us our dimensions for the printer. And so this is a little over 40 feet across. And so one thing is that we could design a huge boom that would reach all the way across, or another one is have a 20-foot boom arm and then just drive the printer around, if that makes sense. And so my favorite option, of course, is the one with the shorter arm. It does make the navigation and orientation in 3-dimensional space a little bit more challenging, but I think mass optimization is so precious that that's the way that we should go. But there is still some debate about that. Some people say you should just park the printer, never move it, and have the arm move around. That way you don't have to worry about the navigation during the build. So that's not my personal opinion, but we're going to debate it and do the trade studies and figure it out. So
do you have to deliver one builder per structure and then you wind up with a piece trapped in the center of the torus? Or can you reuse that piece of, call it infrastructure, if you could in fact transport it to a different location?
Yeah, we have 2 different ideas in case some of this will ultimately be up to NASA, what they want to fund and do and not do. My favorite is the mobile unit that would come outside the torus and print from the outside and then go on and keep printing things. That's an expensive piece of equipment. You should print 100 buildings, not 1. If for whatever reason NASA wants a lower cost piece of equipment without a transportation system, I think we would then shift direction to like, what can you use that for after you're done printing? Can you run telecoms up through it? Can you deploy solar panels from it? If you've got a big pole sticking up, what can you do with it? That is not my favorite option. I much more prefer the mobile construction system, but some of that will be up to NASA. They're the customer, so.
Jason, you brought up the dust again. How would you protect your mechanisms from lunar dust?
This is, the short answer is we don't know yet. And this is probably our most important area of research. And it's very difficult even to research because we don't have any moon dust on Earth. And we're not even clear how we would create a faithful, what you would call mechanical simulant that just like replicates the mechanical behaviors of the moon dust. It's going to be probably a multi-pronged effort. We will need to think about dust avoidance, like what can we just protect from the dust, protect everything you can. And then there's also these like dust resilient mechanisms that are like, sometimes they seem like very dumb and non-space age, but like pulleys with big wheels where you can just like dump dust on it and like almost like avoiding fine robotics, right? That are going to be really too prissy to handle the lunar rover. It's almost like dumb, like caveman style pulleys and mechanisms that are very dust resilient. And then some people are doing some very interesting research on like dust, either dust repellent coatings or the ability to like pulse an electrical shock through the entire system and almost like eject the dust off of it. Like you just accept that you're going to get dust and you find a way to remove it. So dust removal, dust protection, and then dust resilient, like combining all 3 of those strategies will hopefully get us far enough. But if you had to ask me, Jason, what keeps you up the most about the whole project, or if it fails, why do you think it's going to fail? It would be dust. So if it's the craziest thing in the world, it would be the dust.
Great, thanks.
Okay, I've got another question. So your machinery is going to need a lot of power. How do you
Yes.
propose to supply that power?
So on the CLIPS, our early missions on the CLIPS landers, we've designed the one that I showed you the picture of earlier, which is a little robotic arm off a CLIPS lander doing a demonstration. We've designed that entire mission, both the subsystem and their ConOps, or the concept of operations, to use the onboard power. We can complete all the demonstration with the onboard power that the battery and solar systems that the CLIPS lander will provide. In the long term, I also do worry about this one a lot, Stokes. Every time we ask NASA about it, like, hey, what are our power requirements? How much are we going to have available to us? They keep telling me not to worry about it. It'll be there when I need it. But of course, I keep worrying about it. But I'm a big fan of nuclear, to be perfectly frank. Solar's okay, but there's a really long lunar night. I hope that we'll see in the next decade the rapid development of like small scale nuclear power systems for the moon and Mars. I think it would just really expand our capabilities.
So you're proposing to get power from other sources?
Correct. Yeah, NASA is saying they're going to have a lunar utility that everybody gets to use, right? The excavators get to use it. The construction teams get to use it. The research teams get to use it for the landed habitats. But you start adding it up, it's like, that's a lot of power. And so I hope it actually is there. But that said, we have tried to engineer our system to be as low power as possible. As I said, we have centered building materials with as low as 80 watts, which is about like a single light bulb. Now, the trade-off for that is you go very slow at 80 watts. So that's what you would trade speed for power. If you can give me 2 kilowatts, I can go very fast. I can use an array of lasers and go like really fast if I've got 2 kilowatts. But we can operate as low as 80 watts.
Jason, what are the next steps in your development path?
Our next steps in the development pathway, the very next step is dirty TVAC testing. So both the laser that I showed you and the like melting extruder assembly, we're going to put into dirty TVAC, and we're going to get them very hot, very cold at a hard vacuum with some dust in there, and make sure they can perform and deliver specimens that are of sufficient building strength and quality. So that's the next big development path. The next step after that is doing that. We're actually right now scheduled to be on a Blue Origin suborbital flight, where the flight path and trajectory will simulate lunar gravity. And so we'll put it all in a thermal vacuum in a Blue Origin capsule at lunar gravity and simulate it there. So we'll add lunar gravity to the things we've demonstrated. And then from there, we demonstrate the subsystem on the lunar surface. And if all that goes well, all of those pathway things go well, then we'll hopefully receive funding to develop the full Olympus construction system. So that's kind of what's up. And so that Blue Origin flight is next year, if all goes well. Well, more like 18 months from now. My head is already in 2022. It's in 2023. And then that lunar surface test is in 2026. And I think we could have assuming there's no funding hiccups and no political, sometimes NASA does these things where we're going to the moon. No, we're going to Mars. No, we're going back to the moon. Assuming none of that happens and we hold the course for the decade, we could easily have a full-scale Olympus. I shouldn't say easily. None of this is easy. It's conceivable that we have an full-scale Olympus construction system on the surface of the moon in the 2020s, in the very late 2020s.
So Jason, I know that you have constructed the analog at JSC, and everything that I've read about so far, the studies that are planned to be done in there seem to revolve primarily around food systems and microbiota and things like that. But are you going to be collecting, or will you be privy to any of the data that's generated with respect to habitability and behavioral performance?
We will, and as you can imagine, some of that information will be interesting from an architectural perspective. And any changes in architecture could potentially say we need the system to be different or operate differently. And so we will be following this very closely and incorporating all of the feedback from those missions into our continued engineering designs. But you're absolutely right. The primary focus is on just like human health and performance. But we're going to get all the auxiliary data we can to make all the good decisions that we can.
Do you have any specific research that's targeted at that, or is it going to be ancillary data?
No, what they've said is as they're interviewing, the number one, they said we can have access to the data that they'll be collecting. But I don't know what all that will be yet. And they said, like, as they do like debriefing and question asking to the crews, that they would allow us to submit sort of the kind of questions and things. I suspect they'll be very qualitative, like, you thought this was tall enough, but I felt very cramped, or the material was too rough. Is there a way to process it so that it's even smoother? Or, you know, I think they'll be very qualitative in that way. The building won't be subjected to the kind of like structural forces or environmental forces that you would expect on the moon. And so it'll be really like, how did the humans like it? Living in a big 3D printed structure for a year. What was good that we can do more of? What was bad that we need to scramble and figure out a way to change so that it's psychologically bearable? If that makes sense.
Yeah, well, I think habitability is extremely important, particularly for those long duration types of missions. And, you know, don't discount the usefulness of qualitative information.
Well said, and thank you for the encouragement.
So Jason, where is the GSA analog being built? What building is that?
It's
Do you remember?
building, I believe it was building 5. It's funny, I was there every day for weeks. You think I wouldn't forget it. 510A, I believe, is the building. It's the same building we found out later, which was really cool, where they developed the X-37 space plane. It's very much at like the back of the campus. And that's
220.
220. Thank you. 220. There it was.
Well, and just for everybody listening, I'm hoping to arrange a tour of your facility in 220. And you know, in the pretty close future. So I think it's just, I'm gonna be working with Jason and his firm to enable a tour. If anyone would be interested in seeing that. So is it in a state where we could take a tour now, Jason?
It is. It's just not finished out. So the print is done, but all the outfittings, like the cabinetry, the toilet, sort of all the extra things that have to get put in now are not in yet. But the print's done, and it's still very moving. For me, it's very moving to be inside. So I'd be happy to meet you now or whenever we can all get together. Or I'd be happy to, like, if you want to wait till it's like done, and before they start missions, that would also be a really fun moment.
Right there, you got any idea when that would be, when it's done, but before the mission starts?
So assuming the short answer is that we could be done by now. We're waiting on the like contract to get processed and all that, because they issued it as 3 separate contracts: a design contract, a construction contract, and an outfitting contract. And so we're just waiting on the paperwork that says we can go. And then so the optimistic schedule will be done before Christmas. The pessimistic schedule is like Jan or Feb. But we'll be pretty quick once they give us the green light.
Well, okay, great. Well, I'll be in touch with you about that, because it'd be great to get a tour.
Okay, amazing. Well, thank you, everyone. It was really lovely to get to share with you today. Thanks for the questions. Thanks for the feedback. And truly, thank you for all your work. It's going to take the best of us doing a lot of really good work for years and years and years and years to reach our true potential. And it was an honor to be with you all today.
Well, thank you for this fascinating presentation. I think we all enjoyed it. Yeah, what you're doing is the future. And so I think it was really good to hear this. And your ideas certainly sound doable. And
Yes,
I think
we
we'll all
hope
be.
so.
supportive of you.
Okay, thank you, team. Adios.
Thanks. Okay, I'm gonna stop recording now.